got an equation for another quadric surface up here on the board. Again, we can see that this one is centered at the origin. So let's just look at the trace in each of the coordinate planes. If I started in the xy plane, which has as its equation z equals 0, I'm going to get negative x squared minus y squared over 2 equals 1. Now that has no solution, because this left-hand side here is always going to be less than or equal to 0. The biggest it could possibly be would be 0 if both x and y were 0. But the right-hand side is 1. So there's no solution. So there is no intersection of our surface with the xy plane. Now if you think back to what I said in the directions, I said make sure you look at the planes that are parallel to the coordinate planes and that pass through the center, unless it's necessary to move to an appropriate parallel plane. When you get nothing, so here we get no graph, that would be a good time to move to an appropriate parallel plane. So I'm going to look at some other planes. Now, if I were to plug in z equals plus or minus 1. Now, I want to be careful how I label that. I don't want to call that the xy plane because then I would simply be lying. That is not the xy plane. I want to say that that is parallel to the xy plane. So do make sure that you're labeling things carefully. Now, if z is plus or minus 1, this becomes negative x squared minus y squared over 2 plus 1 equals 1. Okay. Now, clearly I could subtract that over, so I get negative x squared minus y squared over 2 equals 0. Now, that does have a solution. 1. Just the origin in the xy plane. So we're getting a single point. Now, a single point is a degenerate ellipse, but that's not a very interesting trace to have. So I'm actually going to go a little bit further away to try to get to a more interesting trace. I want to try to get to a non-degenerate ellipse, because a degenerate ellipse just gives me a single point. So I'm going to try z equals plus or minus root 2. Now, I don't have to choose those particular values for z. I could choose anything bigger than 1, because that's going to make z squared be bigger than 1, so that when I subtract it over, I'll get something negative. Then both sides will be negative. I can multiply through by negative 1 and make both sides positive. I'm specifically choosing z equals plus or minus root 2, which again is parallel to the xy plane, because that makes my equation really nice. Negative x squared minus y squared over 2 plus 2 equals 1. Now, because I have a 2 here, when I subtract it over, I'm going to get negative 1. So I got negative x squared minus y squared over 2 equals negative 1. If I multiply through by negative 1, I've got x squared plus y squared over 2 equals 1, and it's in standard form. Okay. So I spent a little bit of time strategizing about which parallel plane to move to so that I was able to get something in standard form. But let's say I hadn't thought to do that and I'd plugged in z equals plus or minus 2. Those would also be parallel planes above and below the x-axis. If I had that, then this would become 4. When I subtracted it over, I'd have a negative 3. So I'd just have to divide by negative 3, and that would just change the numbers that I had in the denominators when I got things into standard form. Okay, so I can go ahead and draw this trace. I'm going to write that that x squared is x squared over 1. So that's a 1 squared, and 2 is root 2 squared. This is the first example I've given you where I didn't give you a really nice perfect square in the denominator. We can handle it. Okay, so in the x direction, I'm going to come 1 away from the origin. Root 2 is between 1 and 2, because root 2 squared is 2. 1 squared is 1, 2 squared is 4. Root 2 squared has to be in the middle. I know it's actually about 1.4. Not concerned that you get it exactly, but you should be able to figure out that it's bigger than 1, smaller than 2. So I'm getting a lovely ellipse. So I'm going to have nothing in the xy plane. If I go up or down 1, I'm going to hit a single point. If I go up or down more than 1, I'm going to start to have non-degenerate ellipses. Okay, so let's take a look in the xz plane. So for the xz plane, that means y is equal to 0, so that's going to kill off that term. So I'm going to have negative x squared plus z squared equals 1. I might choose to rewrite that as z squared minus x squared equals 1, just because I'm used to having the positive term first, although I don't need to. So here we're in the xz plane. And remember, that positive term can't be 0. So z can't be 0, but z equals 0 would be the x-axis. So that tells me that my hyperbola is going to have a top and a bottom branch. Now, both of these I can write as over 1, which is just 1 squared. So from the center at the origin, I'm going to come up 1 and down 1, and that gives me my vertices. Then in order to figure out how narrow or wide to make those branches, I'm going to come 1 over in the x direction so that I can draw in these diagonal lines here, which are the asymptotes for my branches. And so then the bottom branch approaches those asymptotes, and the top branch approaches those asymptotes, and that's the hyperbola we would see in the xz plane. Now, if I look in the xy plane, that's going to have as its equation, not the xy plane, the yz plane. That has as its equation x equals 0. So the equation that we're getting is negative y squared over 2 plus z squared equals 1. Again, I might choose to write the positive z squared term first, although it's not absolutely necessary. That just looks more familiar to me. And again, I can write that z squared as z squared over 1. So that's a 1 squared. And again, that 2 is root 2 squared. I'm actually going to erase this equation, because once I have the traces, I'm going to have all the information I need. Okay, so let's see. In the yz plane, we've got our hyperbola. Again, z can't be 0. This time z equals 0 is the equation for the y-axis. But once again, we're going to have a hyperbola with a top and a bottom branch. So from the center, I'm going to come 1 up and 1 down, and that gives me my vertices. Now, in the horizontal direction, I'm coming root 2 over to the left and to the right, so that I can draw in the asymptotes. I didn't draw that very well. Let me clean that up just a little. That looks a little bit better. Okay, so there's our top and bottom branch of that hyperbola. All right, so we are ready to sketch things. So notice, once again, we've got 2 hyperbolas and 1 ellipse. This is the oddball. I'm going to draw this 1 second. That rule, I'm pretty much always going to follow, except for the one weird case, which is the last one that we'll get to. All right, then, if possible, I like to start in the yz plane. So I'm going to draw my hyperbola in the yz plane like so. Okay. And now I want to draw my ellipses. The ellipses I'm going to be drawing in these parallel planes, because here's the xy plane. There's going to be nothing here. If I come up to 1 and down to z equals -1, those are the single points that we're going to be getting that we got in the plane z equals plus or minus 1. If I go higher than that, that's when I start to see non-degenerate ellipses. So I'm going to see something that looks something like this. So it's like I have a bowl and an upside down bowl here. Okay. And then I can go ahead and draw in the xz plane. I would also have a hyperbola. Notice the front part, I'm drawing a little bit to the left of the back part. So we'd have something like that. And then I can draw in my axes like so. This is something that we call a hyperboloid in 2 sheets. So the last shape we had was a hyperboloid in 1 sheet, and I said that name would make more sense after we'd seen this one. This one comes in 2 separate pieces. The hyperboloid in 1 sheet came in 2. Okay. I'll also point out that if we look at the equations, this equation was -x squared minus y squared over 2 plus z squared equals 1. Notice when it was equal to 1 and all the squareds were on this side, we had 2 negative signs. If you look back at the example for the hyperboloid in 1 sheet, when it was equal to 1 and we had all the squareds on one side, we had 1 negative sign. So that's a nice way that you can tell just by inspection, 1 negative sign, you're going to be getting a hyperboloid in 1 sheet. 2 negative signs, you're going to get a hyperboloid in 2 sheets. It is necessary that it be in standard form equal to 1 before you start counting your signs. Okay. The reason for that is that with the 2 negative signs, if you kill off the third term and it's equal to 1, you've got something that isn't positive equaling 1. That's going to give you that there's a plane that you don't intersect at all. Whereas if you only have 1 negative sign, then in the if you kill off the term with the negative sign, you've got 2 positive squareds that you're adding together. That's going to give you an ellipse. Okay. All right, I will also point out that here the oddball was the z. 2 negatives, 1 positive, the one with the different sign was z. This was centered on the z-axis. If you look at our last example, where you had 2 positive signs and 1 negative sign, the oddball in that case was also the z, and it was also centered around the z-axis. So whichever sign is different from the other 2, that's going to tell you which axis passes through the center. So there are some nice shortcuts for being able to tell the type of shape you're going to get. I can just look at that and say, oh, that's a hyperboloid in 2 sheets centered on the z-axis, so I know it looks something like that without even drawing these traces. Okay. Now, the traces help me to be a little bit more accurate and confirm that work, okay? But there are some things to be aware of, and it's kind of nice to be able to double check that. If I notice that, hey, that's the oddball, but I had drawn something so that it was centered around the y-axis, I'd say, oh, I think I maybe did something wrong. Okay. All right.